Our third hydration reaction is called hydroboration oxidation. This was also discovered in the 1950s, and as a result also has a name which describes the structural changes that occurred during the reaction. In this reaction, we start with an alkene, and we first treat it with BH3, which is called borane. Now, BH3 itself is a gas, and actually it exists when it's pure as a dimer where there's 2 borons and 6 hydrogens arranged, and in fact this is one of the circumstances where there are actually 2 bonds to each hydrogen bridging between the borons. It's a very unusual structure. It's been very studied. What we can do, however, is we can put in a solvent. This solvent is tetrahydrofuran. We're going to learn its structure in a later chapter, but basically it has an oxygen that can interact with the boron. So when we put diborane, in other words B2H6, and we take it and we bubble it through tetrahydrofuran, we get a solution of borane interacting with the tetrahydrofuran separated. And so this is the reagent that we will use. Because it's a liquid rather than a gas, it's much easier to work with. We then, after allowing the borane to react with the alkene, we treat that product with hydrogen peroxide and sodium hydroxide. The result of this will be, again, that our molecule will have had its double bond converted to a single bond, a hydrogen attached on one side, and a hydroxyl group on the other. Let's take a look at our mechanism. Our mechanism has several steps, and in fact has a part 2. So in the first step, the borane reacts with the alkene. Now this reaction is a fairly complicated reaction. It all occurs in one step. It's what's known as a cycloaddition. The alkene is attracted to the boron, which has an empty space because it only has a steric number of 3. The double bond breaks, it comes out and makes a bond to the boron. At the same time then, the carbon during this process gains a positive charge. The hydrogen, this bond, is attracted to that positive charge and it moves down and simultaneously makes a bond to that carbon. So that essentially we move a pair of electrons up here, and then we move a pair of electrons down here, and we end up with this product where on one side we have a bond to hydrogen, and on the other side we have a bond to boron between the carbon. This can actually occur as many times as there are hydrogens on the specific boron. So it's possible to end up with a boron in the middle, 3 carbons with hydrogens attached to it. I'm just showing one. After that's over, we take that organoboron compound, in other words, the compound that has carbon attached to boron, and we treat it with hydrogen peroxide and sodium hydroxide. It does a rather complicated rearrangement reaction, the result of which is that the boron is replaced with an OH hydroxyl group. I'm not going to teach you the mechanism of this because it's rather advanced, and I don't think it really helps you understand the reaction very much, with the exception of possibly explaining the stereochemistry. So you'll probably just have to memorize that this replacement goes with what we call retention. If the boron is on a wedge, the OH is on a wedge. If the boron is on a dash, the OH is on a dash. With regard to regiochemistry, the regiochemistry is anti-Markovnikov. This can be understood by looking at the structure of the borane reagent. Boron has a very low electronegativity, so it actually is the electrophile. This is different from the acid reactions where the hydrogen is electrophile. It's going to add to the less substituted carbon so that the partial positive will be on the more substituted carbon. We can sort of imagine this by doing an imaginary reaction where we break the addition down into 2 steps. You need to understand, however, that this is not how the reaction proceeds. It actually proceeds in 1 step. In our imaginary reaction, we would imagine that the pair of electrons from the pi bond breaks and makes a bond to boron. In that case, there are 2 directions that the boron could be attached. It could either be attached here on the more substituted carbon, which would create a secondary, less substituted carbocation, or it could be attached on this side to the less substituted carbon, which would create a tertiary, more substituted carbocation. Between these 2 possibilities, this one should be preferred. So therefore, we expect, as this reaction goes uphill in energy, we expect it to be faster to make this type of intermediate. It actually doesn't make this intermediate, but in the transition state, we'll pick up elements of this. Then the hydrogen just moves down onto the positive charge, and therefore we get the hydrogen attached to the more substituted carbon. Then when we replace the boron, the oxygen would be attached where the boron was attached, to the less substituted carbon. Having the hydrogen on the more substituted carbon is anti-Markovnikov. Markovnikov said the hydrogen should prefer to add to the less substituted carbon. In this case, it occurs because the mechanism is different from the mechanism of the reactions that Markovnikov studied. The advantage of this is that now, with a given carbon-carbon double bond, we can selectively make either possible regioisomeric product. Sometimes we might need one, and sometimes we could make the other. This reaction has stereoselectivity. It proceeds specifically with syn addition. The reason for this is that the first step is what's known as a cycloaddition. The boron and the hydrogen, which are attached together, they add simultaneously, which forces them to add from the same face, since it's not possible for the boron to reach through the molecule to add the hydrogen on the other side. So our first reaction is a syn addition. We get boron attached on one carbon, and we get hydrogen attached on other carbon, but they come from the same face. So, as we discussed, when we do syn additions, we can get either syn addition from the top or syn addition from the bottom. So we should get a 50-50 mixture of these 2 stereoisomers. The important part about this stereochemistry is that when we replace the boron, it is replaced with retention. So if we look at this molecule, for example, the boron is here attached to what used to be the top face. When we replace it, the OH will be attached in the exact same location as the boron, so that the OH and the H are still effectively syn. They're still effectively attached to what used to be the top face of the molecule. Similarly here, the boron would be replaced with a OH on the bottom face, so they would stay syn. So, as we pointed out, in these syn and anti-reactions, because we can approach from 2 different directions, we get a mixture of mirror images at the carbons that are formed. In this case, because there are no other chirality centers, these would be enantiomers of each other.